Now, in a previous lesson, when we were looking at using clinical conversion factors, we noted for the first time a conditional relationship. We're going to see a similar case for density. Let's first talk about what density is first, and then we're going to show you how we can use density as a conditional relationship to solve problems related to density, mass, and volume. First of all, density is defined as the mass of an object divided by the volume, that is the space that it occupies. Mass and volume are two completely different things, and they're measured in different ways. You measure mass by placing it on a balance and reading out the mass in grams, right? That's the SI unit for mass is grams, given by the symbol G. All of this you should know by now. Volume is measured in units of milliliters, where the SI unit is the liter. We measure volumes for liquids typically in liters or milliliters. For solids, we use cubic centimeters, cubic meters, things of that nature. Now, the volume of any solid object can be measured by water displacement. This is Archimedes' principle. So let me just briefly mention how that works. You're going to be doing this in the laboratory next week. If I take a container and fill it up to some mark with water, or really any liquid, and let's say that we have rulings on here that allow us to measure the volume of our water here. In fact, let's say this is the 10.0 milliliter mark. So what I've done here, I've got a container and it has 10.0 milliliters of water in it. And now I'm going to take an object and I want to measure the volume. Well, what I do, using Archimedes' principle, is put this object in here. What's going to happen? The object takes up space where the water was, so that the water level rises. Let's say it goes up to here. So here we've got our little object, and I'm going to say that the rest of this is water, and the height went from 10.0 milliliters, let's just say, to 12 milliliters. The volume of liquid displaced by this little bar is the difference between the heights here. You started at 10, you ended up at 12 when you put it in there. So the volume here of our object is 2.0 milliliters. You just take 12 minus 10 to give you 2 milliliters. So that's how water displacement works, and it was invented historically by a fellow by the name of Archimedes. Now, the common units for density then is grams for the mass divided by milliliters for the volume, or we just say grams per milliliter, or grams per cubic centimeters. This is true. This is something that you were told you needed to memorize when we went over volume, right? A cubic centimeter equals 1 milliliter. Now, this mass-volume relationship will become a conditional relation. We'll take a look at that on the next slide. Let's take a look at a couple of properties associated with density. Oil floats on water. Why? Well, when we look at the density of oil, in this case corn oil, it has this is the mass associated with 1 milliliter at this temperature. If we look at the same for water, water's more dense. So the corn oil floats on water because it's less dense, meaning that there's less mass packed into the same space as in water. So in the presence of Earth's gravitational field, there's a stronger tug on the water than on the corn oil. So the water drops to the bottom, corn oil floats to the top. Why does ice float on water? Well, Solid ice has the unusual distinction of being less dense than the liquid. This is usually not the case. Usually in a solid, the matter is packed more tightly, excluding space better than in a liquid. So there's more ordering, and usually there's all of the space is packed by the matter. Well, there's a special property associated with water, and we'll explain this later when we get to intermolecular forces, but ice actually expands, or I should say water expands when it forms ice. This is why you're always told in a very cold day when you're below freezing, not that that happens very often here in Valdosta, but when it's below freezing, it's a good idea to run water through your pipes and to keep the cabinet doors open, to keep it warm so that the water in the pipe doesn't freeze and expand and burst the pipe. Then finally, your book makes mention of, in a clinical setting, it's not the density of a substance that's usually reported. Like, for example, saline solution will be reported with a certain specific gravity. And specific gravity has no dimensions. It's density over density, but it's the density of a substance, whatever it is you're talking about, divided by the density of water. But the density of water is roughly 1 gram per milliliter. Okay? To measure it very accurately, you have all these significant figures at 32 degrees Fahrenheit, and actually the density decreases with temperature because of the kinetic energy of the water molecules that you're giving, gives them motional energy, and they tend to spread out just a little bit more. So again, you should just remember what specific gravity is. It's the density of something divided by almost 1 gram per milliliter, the density of water. So they're about the same thing. Now let's look at density as a conversion factor. So what do we mean by this? Well, like I said, you've already seen this before in the lecture video that I gave you on solving the patient dosage problem. If you ask the question, what is the mass associated with 1.0 milliliters of water? So this measurement is volume. And we're asking, what is the mass in grams of that? Well, if you took a volume, you measure out 1.0 milliliters of water and went to go weigh it on a balance, this is the answer you would get. So you could take this measurement. Now you take the ratio of the two and you get the density, which I told you will be roughly 1.0 grams divided by 1.0 milliliters. So water has a density of roughly 1 gram per milliliter. Now, we end up with this equality. This is volume, and this is mass. They certainly are not equal to one another. So this is an example of what we call a conditional equality. What you do is you put the word if in front of this. If you were to measure out 1.0 milliliters volume of water, and then you went to go weigh it on a balance, you would find that it weighs 1 gram. So there is a relationship here. We're talking about the same amount of water measured two different ways. This way we measure the volume, this way we measure the mass. And so it is a conditional relationship. Now, if I divide both sides by 1.0 milliliters, I end up with the density, right? This mass to volume ratio. So again, density of water is 1 gram per milliliter. Why? Because this is true. Now, we can use this to solve chemical problems. Let's look at another substance, the density of lead. If you were to go out and weigh out 11.3 grams of lead, and then measure the mass of this lead using the water displacement method that I talked about on the previous slide, you would find that you would get 1 milliliter of water displacement, which is a cubic centimeter of lead. Now, what if you're given this problem? If you have 4.0 cubic centimeters of lead, how much does it weigh in grams? In other words, what is the mass? This because of the unit, is volume. You need to know this. Okay, anytime I give you a unit like this, you need to think, oh, that's volume. If I give you grams, you need to think, oh, this is mass. Now, if you look at the relationship, you can look at this as a ratio. 1 cubic centimeter of lead is to 11.3 grams of lead, as 4 cubic centimeters of lead is to how many grams of lead? Well, you just need to take this mass and multiply by 4, and you'll get the answer. Okay? So you could do this just by looking at the ratios. Using the unit analysis method, you would do it this way. You start with your input. This is it, 4 cubic centimeters. Where am I trying to get to? I'm trying to solve for the mass in grams. So you would start your problem here. This is your input. This is your output. This is what you're solving for. You just don't know what this is. So we need to construct a conversion factor that's going to do it. Well, we're going to generate that from the density, from this relationship right here. Now, there's 2 conversion factors we can construct out of this. The one we want is with cubic centimeters of lead in the denominator, so that cubic centimeters of lead cancels. The unit that we want here is grams of lead, so we want that on top. So we put it in like this. Cubic centimeters of lead cancels, and we get an answer when we round to 2 significant figures, right? This is 2 significant figures. This is 3 significant figures, and this 1 is exact. So it doesn't even enter into our thinking. So we should round to 2 significant figures to our final answer. All right, so that's another example of how you can use even a conditional equality. Even though it's not a true equality, you can generate conversion factors that allow you to go from one thing to another. Now, there's another way to solve this problem. You note that this is volume. So I'm going to write this, a symbol for volume as the letter V, multiplied by, well, what is this conversion factor? Well, it's the density. I'm going to use a small script d to denote density. And what do we get out? The mass, which I'm going to write as small case m. So we have an equation. Volume times density equals mass. It's something we could memorize even if we wanted to, right? But I'm going to show you on the next slide that's not something you're going to want to do. Right? So in the previous problem, I showed you how to solve information that's given to you related to density by using the unit analysis method. Now we're going to show you another way, and that's from a definition with an equation. This definition, density is equal to mass divided by volume, that is something that you ought to memorize. Why? Because it's a definition, right? All definitions in chemistry you're going to want to remember. Now, what this means is, if I am given in a problem the mass of an object and its volume, I put the mass in here in grams, I put the volume in here in whatever units I need, milliliters or cubic centimeters or liters or whatever, and I take the ratio, I will get the density. Okay, so you would start by memorizing this, get mass and volume, I could calculate density pretty easily. What if, like on the previous problem, we showed you that if I have the density and the volume as my inputs, it's possible to solve for the mass. Now it looks like I've got an equation here to memorize, but you don't. Here's why. You memorize this one because it's the definition. And if you do algebra on each side of the equation, the algebra that you're doing is you want to solve for the variable of interest. Now, I've got mass over volume on one side, density on the other. If I want to solve for mass, I need to have mass variable isolated by itself. To have mass on this side and volume removed, I need to multiply by volume on this side, so that volume divided by volume cancels. Well, with the equation in algebra, whatever I do to one side, if I do it to the other side, I don't change the equality, right? So now by multiplying both sides by volume, I have a new equation. Mass is equal to density times volume, which is the same thing we generated here, right, by using the dimensional analysis method. We could do the same thing by starting with our definition. If I'm given volume and density, right, and I'm told to solve for mass, just rearrange this equation that I memorized. Generate a new equation. You don't have to memorize this one. You can get it from doing the algebra. Conversely, what if in our problem we're given the mass as input and the density, and we're told to solve for the volume, right? So these are things that we're solving for. Again, I could start with my equation here. Density is equal to mass over volume, and we need to solve for volume, right? So if I start here, do the algebra to isolate volume. Well, we start by multiplying both sides by volume, so that cancels. So now I'm at this equation, right? Now, to get volume equals something, I divide both sides by the density. So I'll multiply this by 1 over d. This cancels, and I get volume is equal to the mass divided by density. So this is how I recommend that you do all of your problem solving in chemistry. When you have an equation that's given to you as a definition, you have three relationships between density, mass, and volume. You've got your definition, and then you can solve for mass or volume by doing the algebra as needed. So you can look at this comment here. You've got three formulas, but you don't need to memorize them all. Memorize this one and do the algebra as needed to get mass or volume. You're just using one strategy that we apply over and over. It's actually, in this case, from the definition, you're using one strategy. We're not even using unit analysis here, but we could have done it that way as well. Let's look at a problem dealing with this. A platinum ring, in quotes, purchased from eBay for $243. Note that we have the dot there, indicating that we have three significant figures, is placed on a balance. The ring has a mass of 5.84 grams. The ring displaces, very important, this amount of water. Now, look at the units. That is volume. You need to know that. You need to know that grams, this is mass. It's really one of the first things you should pull out of this. Now the question is the ring made of pure platinum? You're given the density of platinum is 21.4 grams for every cubic centimeter of platinum. Now, first step, write down what you're given. We don't want to have to look at all this language again. The fact that it costs $243 is not relevant to solving the problem. What is relevant is the mass and the volume. So the mass directly is 5.84 grams. Now, when you read this displaces this amount of water, this is a volume. This is the Archimedes method of determining the volume of a solid, right? So this is the volume of the solid, of the ring. Now, to solve for the density, right, we're given mass, volume as inputs. This is the output that we're seeking. You would write down the definition for density. That's where you're going to start. There it is, okay? So we know that, we know that. We want our units for density to be grams per cubic centimeter because we want to compare this density with the density for pure platinum. So, it's pretty simple, folks. We put in our mass, we put the number and the unit, divided by the volume and the unit, cubic centimeters, and we have three sig figs here, three significant figures there. We need to report to 3 here, so it's 10.5 grams per cubic centimeter. Now, compare the density of our ring with the density of pure platinum. Clearly, this ring is made of something else other than platinum. It might have some platinum in it, but it sure isn't pure. A lighter metal has been put into it. Okay, so we know that the ring cannot be black.